We're going to take a look at conic sections, and while you've already explored circles in depth, I want to give you the definition so that I can draw a parallel to the definition for an ellipse. A circle is a set of points equidistant to a given point. The given point is the center and the distance is the radius. When we represent a circle in the xy plane, we often give it the center coordinates hk and a radius of r. And using a distance formula or Pythagorean theorem, depending on your perspective, our equation is x minus h the quantity squared plus y minus k the quantity squared is equal to r squared. X and y are the set of points. That defines a circle. We're going to quickly move on to the parabola. A parabola is a set of points equidistant to a line and a point not on the line. The line is called the directrix, and the point is the focus. Here we have a parabola and its directrix, and we can see that the directrix is 2 grid squares off of the vertex of the parabola, and so the focus is also 2 grid squares off. We have here the focus. We're going to label that with coordinates p, 0. I'm going to make that a lowercase p. And the directrix is going to have an equation. It's a vertical line, so it has an equation that starts with x equals. And since the distance from the focus to the vertex is the same as the distance from the vertex to the directrix, this is going to be x equals negative p. We have the y-axis pointing up and the x-axis pointing to the right. Now, this statement about the set of points that are equidistant to a line and a point not on the line means that for any point on the parabola, the distance from the focus to that point will be the same as the distance from the directrix to that point. And what defines the parabola is it doesn't matter what point we use on the parabola, those two distances will always equal each other. So picking one point on the parabola and calling it xy, and then labeling the distance between that point and the focus d1, and then the distance between that point and the directrix d2, we can say that d1 will always equal d2. Now d1 can be expressed as the distance between 2 points. The points have coordinates xy and p0. Therefore, d1 is equal to the square root of x minus p the quantity squared plus y minus 0 squared, so just y squared. On the other hand, d2 is going to be whatever the x coordinate is, that's the distance from the y-axis, plus an additional p because the directrix is 2 units to the left of the y-axis. Therefore, d2 can be expressed as x plus p. I'm going to color code this a little bit here. So we have d2, which is the horizontal distance from the directrix to the point, and then we have d1, which is the distance from the point on the parabola to the focus. There we go. That looks much better. Now, simplifying inside of the radical and then squaring both sides to get rid of the radical will give us x squared minus 2xp plus p squared plus y squared is equal to x squared plus 2xp plus p squared. We see that we have some like terms on both sides that we'll subtract out. We end up with y squared is equal to 4px. This is the equation of a parabola that opens to the side. Well, right or left, depending on the sign of p. I think I was premature in putting a box around that because there's a lot more that I want to write. Namely, just as a circle whose center is not at the origin has a center at hk, and that hk shows up in the equation of the circle, we can also express y minus k the quantity squared is equal to 4p times the quantity of x minus h. And this is the equation of a parabola that opens left or right, again, depending on the sign of p. And its vertex, the bendiest part is called the vertex, is at coordinates hk. Another way to say that it opens left to right is to say that it is a horizontally oriented parabola. Vertically oriented parabolas have similar looking equations. X is the one that is squared for a vertically oriented parabola. Notice I've kept, for the translated parabola here with hk, x minus h is showing up in both of these, x minus h, and y minus k is showing up in both of these. And in all of these cases, the vertex has coordinates hk. Now I'm going to copy this picture and paste it down here because I want to keep drawing on it, but I didn't want everything to get out of hand. Folks, we're saying that the distance between the focus and the vertex is p. The distance between the vertex and the directrix is p. If we then think about a line that goes through the focus and is parallel to the directrix, then it has points of intersection with the parabola, and the distance between that either of those points and the directrix is going to be 2p. Therefore, the distance between that point and the focus will also be 2p. Likewise, the other point that's below it, opposite it. The segment that connects these 2 points and goes through the focus of the parabola is called the lattice rectum. Its length is 4p, and that's called the focal diameter. If we've seen the equation of a parabola, then we know what the value of p is. Therefore, we know what the value of 4p is. And if I know where the focus is, again, I will because I know what p is, then that gives me an easy way to draw the parabola, because at the focus it needs to have a width of 4p. Knowing where the vertex is, putting those dots, or plotting those points here at the end of the lattice rectum, that'll give me an idea of how wide to draw the parabola. Now, I'm not going to go through a bunch of exercises with you and manipulate these equations with y squared equals 4px, and h and k and all of that. You have done that in previous classes. What I'm going to do is just explore this shape a little bit. First of all, this is in a section called conic sections. And they're so called because they come from a cone. If we take a cone and slice it using a plane that is parallel to one edge of the cone, the shape that we will get is a parabola. So what we've done is we've argued kind of a geometrical algebraic definition here in the xy plane, but there's also a definition that comes from a cone. Of course, if we slice the cone straight across, we'll end up with a circle. Having seen basically the algebraic and geometric descriptions of a parabola, let's see where they show up. One place is in architecture. They often show up in bridges. The Golden Gate Bridge has cables that are in the shape of parabolas, and sometimes you'll see an inverted parabola underneath a bridge. And the reason for both of these being parabolas is the parabola has good load-bearing properties. It's a strong shape. Parabolas also have interesting reflective properties. You've seen them in flashlights and car headlights. And the deal with these reflective properties is if there's a light bulb that's placed at the focus, and I say light bulb, but this would be true of any waves, the light waves will come off in all directions in the paraboloid. This would be a parabola that someone spun, by the way. This is it's called a paraboloid. The light will come out from the center and bounce off of the paraboloid, and it will direct all of the rays to point in the same direction. There are flashlights that you can twist and make the beam wider or tighter. When you're making the beam tighter, what you're doing is you're putting the light bulb into the focus of the parabola. This is known as a reflective property of a parabola. For another reflective property, we can consider a satellite dish. They're also made of a portion of a paraboloid, and the property here is that any waves that come from any direction will bounce off of the paraboloid and hit the focus of the paraboloid. And that's why there's usually an arm there in the focus of the paraboloid that will collect all of the waves. All in all, they're a fairly interesting shape.